Morning, everybody. Sorry I'm late. Can you hear me?
Yeah.
Thank you. Appreciate it. All right. Well, let's get started here. Whoops. So just about the test the other day, if anybody has any questions that they want me to look at, I'd be more than happy to do so. There was a question at the end that allowed you to show your work, but you know I don't usually review it unless people ask me to. If I'm being completely honest. So if you've got requests of that nature, please let me know. Most people tend to anyway, but we can go down that road. All right, so we're going to be looking at titration curves right now. And titration curves, I don't know if we actually do any titration curves in lab. I don't think we do these days. But what we're usually talking about here, it says titration of something with something else. And it's actually pretty easy to tell what's what. You've all done titrations before, I know this. Oops. Just trying to enlarge this canvas here. Not letting me. All right. And what we're talking about is the adding of something to something else using a burette. So this could be a burette. And then you've got a flask. And you've got something in here, which I'm calling A, and something in the burette, which I'm calling B. And in that situation, we're titrating A with B. So initially, all you have is A. And what we have is generally a titration curve that looks something like this, where we've got volume, and specifically it's volume of B that's being added. This would be 0 down here, which means that at that point, there's only A in the flask. Over here, we've got pH. Now, pH, we're going to be talking about a bit later as to exactly what that is. But pH is the negative log of the hydrogen ion concentration.
Professor Musgrave?
Yes.
I think you mean to be sharing your screen.
I'm not sharing my screen.
No.
That would probably be a good idea. Thank you. Sorry about that.
It's all good.
This will teach me. So this is the thing. If you don't come prepared, and I wasn't this morning, I'll admit it. I got here late, and then I got all flustered and didn't share the screen. That's on me. You know, I'll admit it. It's on me. Anyway, there you go. So you got A in the flask. You got B in the burette. We've got the volume of B on the x-axis and pH on the y-axis. And the point I'm trying to make here is that it's a logarithmic scale, and logs have to do 10 to the power of something. When we're talking about log to base 10, is 10 to the x. So we're looking at what amounts to here being a logarithmic scale, which is not linear. Log scales are very different to linear scales, and that means we end up with strange-looking curves that we might not see if we were using, say, a regular concentration of H+ rather than the pH. So we do these pH titrations here. So this is an example of HCl plus NaOH. And in this instance, we're titrating HCl with NaOH, which means that we've got HCl in the flask here, and we've got sodium hydroxide in the burette. So at the beginning, which is 0, and I'll just cross that out and I'll put volume of NaOH here because that's what we're adding. At the beginning, we have 0, which means that all we have is HCl. Now, before I go too much further, let's review what we know about the pH scale. This is something that I think most of you are somewhat familiar with, at least. And that's this scale here, where we start out with a pH of, say, 1, and then we can have 5, we can have 7, we have 9, and then we can have 14. And 1 is strong acid. 5 is weak acid. 7 is neutral. 9 is weak base. And 14 is strong base. Is there anybody who's never seen anything like that before? You're all familiar with that? Yeah, well, it's certainly something you'll need to be familiar with, because it kind of underpins everything here. If it's not something that you were aware of before this point, then it's something to be aware of certainly now. I think most of you were certainly aware of the strong acid, strong base, and neutral. You may not have been particularly familiar with the 5 and 9 being the weak acid and weak base, but it makes sense in the context of the table that I have there. But that's just something that we need to be aware of when we're doing these kinds of titration curves. So we're starting out at 0. That means nothing has been added from the burette. I'll say that again. At 0, nothing has been added from the burette, which means the pH is going to be 1. That's the starting pH. Is everybody okay with that? Does anybody have any questions? Now, how do I know that? Well, HCl is a strong acid, right? HCl is a strong acid. Now, you might be wondering, well, how are we going to tell the difference between strong acids and weak acids? Well, as it turns out, I'm actually not that cruel to you. I actually tell you on the test whether something is a strong acid or weak acid, a strong base or a weak base. So it's not something you actually have to memorize, but I will show you something here that will be of aid to you. So we've got a list of here strong acids that I think most of you are familiar with. So sulfuric, this is spelled, this has got the British spelling here. Now remember, I'm not British, right? Some people think I am, but I'm not. It's a lie. Sulfuric, it's with an F here, but anyway, these are all strong acids: sulfuric, hydrochloric, hydrobromic, hydroiodic, nitric, and perchloric. I think most of you are familiar with those. Does anybody have any questions about what we consider to be strong acids? And strong acids are characterized by the fact that when you dissolve them in water, they dissociate 100% into H plus and Cl minus, or H plus and some sort of anion. That's what characterizes a strong acid. Now, weak acids dissociate only a small amount. So this is an example. This is vinegar or acetic acid. Acetic acid will dissociate only 3%. So only 3% of the acetic acid turns into H plus and some sort of anion. And my rule would be, these are all the strong acids, and I want you to consider pretty much anything else to be a weak acid. Now, for strong bases, you'll notice they all have something in common. They all have a metal ion, and then they all have OH as their OH minus as their anion. So these are all what I'm considering to be strong bases, and anything else I want you to consider to be a weak base. And weak bases, likewise. See, weak bases split into OH minus, or form OH minus when you put them in water. And you can see that, for example, ammonium hydroxide, NH4OH, will only split up 2% into NH4 plus and OH minus. So that would be an example of a weak base. So acids split into H plus, OH hydroxide split into OH minus. H plus and OH minus both give water, of course, when you add them together. Does anybody have any questions about strong acids, weak acids, strong bases, weak bases? Okay, so at the moment, for this particular example, what we're dealing with is a strong acid being titrated with a strong base. Okay, strong acid being titrated with the strong base. So what happens is that as we proceed with the titration, the pH begins to go up, and then at some point it goes up. Sorry, let me make that a little bit. There we go. It goes up a bit, and then it jumps, and then it sort of plateaus again after that. So this jump is kind of an interesting thing that happens. The ending pH is going to be 14, which is going to match whatever the sodium hydroxide is. So let's take a look at what's going on. I'm going to show you a little diagram of what's going on. I'm not going to do this for all of them. I'm just going to do this for this particular example. All right, let me get rid of some of this stuff here. I'm not having a very good time here with this selection thing. Okay. So what we're doing is we have our flask here, which I'm going to turn into a beaker. And in this beaker, we have what I'm going to call AH. AH is going to be the acid here, which is really going to be A minus plus H plus, essentially here. And over here, we'll have the BOH, which is our strong base, which is going to really be B plus and OH minus. And what we're really interested in is the interaction between the OH minus and the H plus. Now, for this particular process, and I've got the reaction here in the slide, I think most of you are familiar with this kind of thing where we've got an acid and a base gives water, that's from the H and the OH, and then a salt, which is going to be Na plus and Cl minus, forming NaCl. So it's a standard double displacement reaction that I think you're somewhat familiar with, or should be. So in the flask, we've got our AH. I'm going to put down 3 AHs here, just for kicks. So what happens? We have our BOH, and I'm just going to add 1 in here for now. And what we're going to get is one of the BOHs will react with one of the AHs. We'll end up with AB, which is, well, actually, it wouldn't be AB, it'll be BA. That'll be the salt, because that's the cation. B plus is the cation, and A minus is the anion. And then we'll end up with water as well, which I'm not going to show because the water is in the solution anyway. But the point is that one of the AHs is gone now. What happened to it? Well, it reacted with the BOH. That's what's going on. All right, so I'll add another BOH in. See, what am I doing here? Well, I'm doing sort of what we would do in a regular titration, where we would add B through the burette down into the HCl, and we do it slowly. So we add 1, then we add another one, and we add another one until we get to this end point here. You've all done titrations before, so you're familiar with that concept, I think. So we do another BOH, and it will react with another AH, of course, and we'll end up with BA, BA, and then AH. We'll add another BOH to that. And at this point, all the AH is gone, and all we've got is just BA. This is the end point. This is the end point, and the end point is where the amount of BOH we've added is equal to the amount of the AH that we had here. So in this case, it would be when enough sodium hydroxide has been added to completely neutralize the HCl. And what happens at that point is that the pH kind of goes up because the AH is going down in concentration, so it's becoming less acidic. And then at the end point, the AH is completely gone, and we end up getting this massive jump here, and then it sort of just goes up after that, because all that's being added to the solution at that point, if we add in another portion of the base, is we'll have the BA and we'll just have BOH, because the BOH can't react with anything else. So the pH goes up by a huge amount, and we end up getting this massive jump at the end point here. So the end point is going to be the center of this right here. There's your end point, which I'm going to call EP. All right. Does anybody have any questions? That's generally what happens during a titration. Now, what's important here is that the BA here, which is really like the NaCl, it's that combination of the anion and cation, actually in this case is neutral. I mean, when you add sodium chloride to a solution or to water, it doesn't change the pH at all. I mean, it doesn't make it acidic, it doesn't make it basic. I mean, when you're cooking your pasta, you throw in some of your sodium chloride, some of your salt. It doesn't affect the pH of your pasta. All it does is it just makes it salty. And that's what's happening here in this case when we're doing a strong acid and a strong base. We can actually always estimate the equivalence point very simply by looking at the starting pH and the ending pH and dividing by 2. So we're just sort of looking at the average here between 14 and 1. Well, you know, sometimes I make that 13 just to make the math work out a little bit better. So 13 plus 1 divided by 2 is 7. But, you know, 14 is fine as well. But, you know, it's the point is that it's going to be the midpoint of where we start and where we finish. And we can always tell that because we always know what we're starting with. It's a strong acid, and we know we're finishing with a strong base. So we know that that's a pH of 1, that's a pH of 14, and the average of those two, or the midpoint, is going to be 7. Does anybody have any questions? Any questions? All right, let's take a look at the reverse of this. This would be titration of sodium hydroxide with HCl. So what I'm talking about there, of course, would be this situation where we've got a burette, we've got a flask. In the flask, we're going to have NaOH, and in the burette, we're going to have the HCl. Now, the reaction is, of course, the same as what's going on here, but look at the titration curve. We start out at 14 because all we've got in the flask at the very beginning at 0, and this is going to be volume of HCl here, is going to be 14 at the very beginning, and then at the very end it comes down to 1, which is the pH of what we're adding, the HCl. And of course we end up getting this jump here that goes downward in this case. So it's kind of like a mirror image of the previous one. And there's our equivalence point, which is still going to be 7. pH is 7 at the beginning. So you can see you can see the difference there. It's just a mirroring of the same curve. It's just that we're starting with sodium hydroxide instead of starting with HCl. Does anybody have any questions? Okay. Well, let's look at what happens if we've got a strong base and a weak acid. Now, the strong base I'm using here is going to be sodium hydroxide. The weak acid I'm choosing is acetic acid, which is the main component of vinegar, CH3COOH. I've got it listed as here. Now, let me show you a little bit with the reaction here, because I think that's going to be important. And this is going to be a big deal for the test as well. I really do push the understanding of these reactions and how to figure out what the products are. Now, it's not nearly as bad as you think it is, but, you know, initially you're not going to like it. I guarantee it. But that's okay. So let's say you know that this is a weak acid, and on the test you would know. Why do you think you would know on the test? I said earlier. Anybody have any idea of how you know it was a weak acid?
You're going to tell us.
Because I'll tell you. That's right. Thank you. I'll tell you. So it's a weak acid, strong base. That's right. I'll tell you it's a weak acid or a strong base. Now, if it's a weak acid, what you know is it forms H+, because that's what acids do. And if it's forming H+, then whatever else is with it is going to be negative. So take a look at that. Make sure you understand exactly what I did there. How in the leap of logic that I used to get that far. First of all, weak acid. I thought, oh, okay, that's forming H+. So I took the H+ off, and then everything else became a negative that goes with it. It's kind of similar to what we were doing at the end of test 1, if you'll remember. Does anybody have any questions? So the strong base, we know that that forms OH minus in this case. So it'll be Na plus and OH minus. But I'll get to that in a bit as to exactly how we handle strong bases that don't have an obvious OH minus, but I'll get to that later. Now, what's going to combine with what? Well, we know the H plus will combine with the OH minus. That'll give water. And then we have the Na plus combining with the rest of this, and that gives our other product. Now, this might be a little bit confusing initially. You might say, well, hang on, is this H plus on the wrong side? Don't we usually put the cation first? Well, the thing is, this isn't one of those ionic compounds. It's actually an organic compound. So it's not ionic. So it's not expressed in the same way as an ionic compound would be expressed with the cation first. That's why it kind of looks weird with the H plus over on this side. That still doesn't preclude, though, us figuring out what it combines with on the other side, because the H plus will always combine with the negative species on the other side, which in this case is going to be the OH minus. And then the Na plus combines with the negative species on the other side, and that gives us our other product. Does anybody have any questions? So you're all understanding that completely, huh? I find that hard to believe. All right. So what are we looking at on the titration curve? Well, we're starting out with sodium hydroxide, because that's what it says, titration of NaOH with the acetic acid. So the NaOH is in the flask, the acetic acid is in the burette. So we're starting out at a pH of 14, and the ending pH is going to be 5. And you might, hang on, why is it 5? Well, it's because we're titrating with a weak acid. I told you it's a weak acid here. And weak acids have a pH of 5, which means that we're still going to see that same kind of curve. It goes wee down to here. And then we can also get the pH of the equivalence point, which is going to be the average of those two. Again, it works out better if I use 13, but 9 would be about the equivalence point, so halfway in between those two. The implication of that means that this stuff here must be weakly basic. Because everything here is what's present at the equivalence point. Now remember what the equivalence point is. It's the point at which equal amounts of acid and base have reacted. So at the equivalence point, there's no weak acid and there's no strong base. They've both been reacted. And all we've got is what's over here on this side, which happens to be what's at the equivalence point, which allows us to say, well, everything at the equivalence point must be weakly basic. All right, does anybody have any questions? And of course, after we've reached the equivalence point, all we're doing then is adding acetic acid. So all we're getting is a pH of 5 at the end there. All right, does anybody have any questions? Okay. Now, there's another concept we haven't talked about yet that we will talk about. It's known as a buffer region, and that's this business down here. And I don't really want to go into it too much because we're going to cover buffers a lot more later. I'll give you a very brief idea about what a buffer is, very brief right now, but we will get much more into it later. So let's see, a buffer. A buffer is a solution of a weak acid and its conjugate base. I know I'm going to introduce some terminology here you're not going to like. That's one of them. A weak acid and its conjugate base that resists changes in pH. Upon addition of strong acid or strong base. Now, it sounds like a lot of gobbledygook, doesn't it? I mean, you look at that and you can say, yes, I know all those words, but I don't know what that sentence means. All right. I want you to think about your blood, for example. And one of the things that can happen is that you might have heard of acidosis and alkalosis. And what we're talking about there is changes of blood pH. Acidosis is when your blood becomes too acidic. Alkalosis is when your blood becomes too basic. So you might be wondering, well, how do we prevent that from happening? Because if you hyperventilate, if you just breathe in and out too often, what happens is the amount of carbon dioxide in your blood can increase, which increases the amount of carbonic acid, which makes your blood go down in pH, so it causes acidosis. So you might have heard of people hyperventilating, and that's what happens is that their blood becomes too acidic. Now, what prevents that from happening to a great degree is the fact that in the blood we have a buffer situation. We have a situation where we use a weak acid and its conjugate base to keep the blood pH at a level of around about 7.6 or 7.5, something like that. Blood is slightly basic, but not very much. And it's buffers in the blood that allow it to be kept at a fairly constant pH. So that's what stops our blood from changing our pH. If the blood pH changes, what happens is a lot of reactions in the body don't work properly because they're all dependent on the blood having a certain pH. So that's what a buffer does. It's a sort of a big picture idea of what a buffer is. So it's a solution of a weak acid and its conjugate base. Okay, so let's talk about that term weak acid. So let's say we have a weak acid, AH. Its conjugate base, to get a conjugate base, you remove H+. It's really that simple. And if I remove H+, what do I get? I get A-, and that's the conjugate base. So that's your weak acid, AH. What's the conjugate base? You take off H+. It's really that simple. Is anybody uncertain about how I'm getting A- from AH by removing H+? So I take away the H, and then the charge on the A goes down by 1 to balance out the plus. So that becomes A-. Because if you were to put A- and H+ together, you get AH again. And that, incidentally, is how you get a conjugate acid, is you add H+ to something negative. That will give you that'll give you the conjugate acid. But that's what we're talking about with buffers then. So it's a mixture of AH. So let me go back here a bit. Buffer is then a mixture of AH and A minus. All right, let's talk about the other part of this, that resists changes in pH upon addition of strong acid or strong base. Well, look at the titration curve here. We're adding, what do you know, a strong base, volume of NaOH here. What's happening to the pH? Well, it's flat. It's plateauing. What does that mean? It means it's not changing much. So that's what this buffer region is. As we're adding this strong base here, we're not seeing much of a change in pH. It's flat. That's what I mean by resist changes in pH. It plateaus. Now, why is it doing that? That would be the better question, right? Why is it doing that? Why does a mixture of a weak acid and its conjugate base, why does that actually cause this to happen? Well, this is how it's working out. I'm not going to go into this too much because we are going to talk about this a lot more later. I'll give you a very brief idea of what's going on. So let's say we've got a buffered solution, as I said, was going to be a mixture of A minus and AH. If we're adding sodium hydroxide to it, and I'm just going to add in 1 here, 1 sodium hydroxide, what's going to happen is the sodium hydroxide will react with one of the AHs and form water and this salt, NaA, which really isn't going to really matter too much here. It's really effectively A minus. So we've got A minus, A minus, A minus, and AH. And this conjugate base is a weak base as well. But the point is that by adding in that sodium hydroxide to the acid, all that we're doing is turning that NaOH into A minus. So something that was a strong base is now turning into a weak base. That's really all that's going on. It's being eaten up. But as you can imagine, as soon as we add enough sodium hydroxide to eat up all of this acid, then we still get this big jump in pH, and we end up getting just sodium hydroxide at the end. So the same thing's going to happen. It's just that in the interim, we're going to get this buffer region. Very quick and dirty. Here's what I can tell you about how you know if there's going to be a buffer region or not. You need to have either a weak to have a buffer region. And we only talk about buffer regions really at the beginning. To have a buffer region, we need a weak acid or base and we need to be titrating with strong acid or base. That's it. So what I'm saying is that down here on the x-axis, that needs to be a strong acid or base, and you need to be adding it to a weak acid or base. And if you're doing that, then you're always going to get this buffer region in here. You'll notice on the previous example, look at this. We didn't get a buffer region. Why not? Well, we're not adding strong acid or strong base. See that? We're adding a weak acid down here. So we don't get a buffer region here. We get, see, there's no real, there is a little bit of a change in pH, but it's not a huge amount, but it's still more of a change in pH than we're getting here with the buffer region. So that's how you'll know. I mean, quick and dirty, if because of the definition of the buffer is that it resists changes in pH upon addition of strong acid or base. So you have to be adding a strong acid or base in order to get a buffer region to occur. Now, you don't have to completely understand that now because I will talk more about buffers later, but that just gives you an idea of how to tell if we're going to have a buffer region or not. It's a very, very quick and easy method to determine that. All right, does anybody have any questions? Okay. What about if we have a strong acid and a weak base? So the weak base that we're going to be using here, well, there's two ways of expressing it. Ammonia, NH3, is a weak base, but we can also express ammonia as NH4OH. And if we do that, you see it's NH3 with water, effectively, NH4OH. And it's a bit easier if we do it that way because then we can see the OH minus that reacts with the H plus to give the water, and then the NH4 plus will combine with the Cl minus to give NH4Cl. So that's the reaction that we're looking at. The point is we're starting out at a pH of 1 because we're titrating HCl with the NH3. So the HCl is in the flask and the NH3 is in the burette. So we're starting out at pH of 1. The NH3 being a weak base is going to end up at a pH of 9, which means that our equivalence point pH is going to be 5. And so we get that same curve there, volume of NH4OH. So again, that's a weak base down here. So we're not expecting a buffer region. We can only ever get a buffer region if we're adding a strong acid or strong base to a weak acid or weak base. And that's not happening here. Does anybody have any questions about that one? Now we've got the reverse here. This is the titration of a weak base with a strong acid. And because we're adding strong acid now to the weak base, you can see we get that buffer region. We didn't have that before. The reaction's exactly the same though. And again, we're starting out at pH of 9 because all we have is ammonia in the flask. And then we add the HCl, and then it goes down to a pH of 1, which happens to be the pH of HCl once it's reacted with everything. So same kind of deal, really. Does anybody have any questions? Now, weak acids and weak bases are hard to predict, so we're not really going to talk about those too much because we don't know really what the nature of the product at the equivalence point is going to be, whether it's going to be acidic or basic. So we really can't tell that. And the last thing we need to talk about here is how to select an indicator. So we've all done these acid-base titrations before, and you know what happens is that at the equivalence point, you get a color change. So for phenolphthalein, it goes from a colorless color to pink, right? You've seen this before. So what is the best way to select an indicator? Well, if you know what the common indicator ranges are, and these are the color change ranges, brom cresol green, 4 to 5.5, phenol red, 6.5 to 7.5, and phenolphthalein, 8.5 to 10. You don't have to memorize these. I actually give you these on the test. And if you wanted to select an indicator, what you would do is probably select the one that covered the equivalence point. So it's really that simple. So going back to this one here, the equivalence point is 5. So I'd probably choose brom cresol green. And then for something like this one here, the pH is 7. I'll probably choose phenol red. And then for this one here, where we've got a strong base and a weak acid, this would be a pH of 9, and I would go with phenolphthalein. So it all depends on what the pH of the equivalence point is, and you just pick the indicator if it covers that range. So it's not really too bad. All right, let's take a look at a test question, and I'll also spend some quality time going through acid-base reactions and being able to pick out the product. And I'll also show you how this relates to what we're seeing in the test, which you'll be taking as well, of course. All right. So I'll pick out an old test question here. And of course, the test you'll be taking is very related to this. All right, here we go. So draw a titration curve of strong base LiNH2 with weak acid, acetic acid. So there's your question. Point out any buffer region if there is one. All right, so let's go ahead and see if we can handle something like this. Let's look at the other things we need to do here as well. We need to write a reaction showing the main products in solution at the equivalence point. That's what I'm talking about. What happens when you add the LiNH2 to the CH3COOH? What kind of products are you getting? How do we determine what those products are? And then we can talk about the starting pH, the ending pH, and what indicator you'd use. Okay, let's look at the titration curve first. All right. I don't think I can write on that. Let me bring my thing here. There we go. Okay. So we start out with our titration curve. We're going to have pH over here. Now, what do we put down here? Can anybody tell me volume of what? So what goes down here on the y-axis? Sorry, the x-axis, I should say. Is it going to be the LiNH2 or the CH3COOH?
The CH3COOH.
So how do you know that?
Because that's what we're adding to titrate with.
How do you know that? How do you know that that's what you're adding?
Because we're titrating with a weak acid.
Right. So the weak acid's in the burette, right? That's what we know.
Correct. Yeah.
Is everybody okay with this? Does anybody have any questions? I'm hoping Kyle was the only one who knew that. Is there anybody who has any questions about this? Being able to tell what goes on that x-axis. So we're starting out with a strong base, LiNH2. How do I know it's a strong base? How do I know it's a strong base?
Stated.
What's that?
You stated.
Where? Where did I state that? I don't remember stating that. Where did I state that?
For strong base LiNH2.
Oh, you mean up here? Oh, I actually said it? I did, didn't I? Wow, okay, it's a strong base. That means we're starting out at pH of 14. See, I didn't have to memorize anything, did I? No, it's in the question. There it is. So it's pH of 14. Where's it end? What's the pH, the ending pH going to be? Any guesses?
5.
0.
5. Why is it going to be 5? I heard a female voice in there. I'm not sure who said it.
Because it's a weak acid. Like, I just remember 5 being from the other problem we did.
Okay, but how did you know it was a weak acid?
You told us
Where?
in the problem.
Oh, in the problem up here, where I said it was a weak acid? Yeah, that's right. Okay. So what's it going to look like? Okay, the curve's going to look like this. Now, is there going to be a buffer region? Oh, that's a bit of an advanced question, isn't it? The answer is no. There is not going to be a buffer region. And the reason for that is because we're not adding a strong acid. This is a weak acid. Remember, in order to get a buffer region, we need to be adding a strong acid here. And that's not happening. So there's no buffer region here in this one. The equivalence point is going to be 9. All right. And that's what the titration curve looks like. Does anybody have any questions? All right, let's look at the reaction here. So we've got LiNH2 plus CH3COOH. Now, I've already told you that this is a strong base and that this is a weak acid. And the fact that it's an acid gives you a huge clue because you know, well, it's going to form H+, and the rest of it, which will be CH3COO-. So look at how I did that. I just took out the H+, and I made whatever else was with it negative. Anybody got any questions about that? The other pattern I can pretty much guarantee for you is if you've got a strong base here and it involves a metal ion, the metal ion will have the positive charge on it and the rest of it will be negative. So take a look at that, make sure you understand exactly what I did there. Anybody got any questions? So what's going to combine with what? Well, the NH2 minus will combine with the H plus, we'll get NH3. And the Li plus combines with the other one, the CH3COO minus, and gives us LiCH3COO. So that's how we know what the products are. Does anybody have any questions? Okay. And the indicator, what indicator would we use? Well, see, I've got the list down here. I'd go with phenolphthalein because it covers the equivalence point, which is going to be 9. Does anybody have any questions? Anybody got any questions? I've got 9 people here today? Jeez. I think that includes me, so it's really 8. You guys are diehards. I don't know. The rest of you must be sleeping in, I suppose. You might watch it later, maybe.
How did you get the NH3 plus again for the product?
It's not NH3 plus.
Oh, sorry, I guess I read that wrong.
The plus is between
Oh,
these two,
okay.
right?
Okay.
So no, it's not NH3 plus. It's NH2 minus, and the H plus gives NH3,
Yes,
and the plus there is an addition, not
I
on
got it. Yeah.
the thing. All right, okay. Let's take a squiz at the quiz. That even rhymes. Let me see how far I had to get today. I think I just had to do titration curves today, I believe. Let's have a look. Yeah. Okay, good. All right, let's continue on here. All right, so this is the actual test you'll be taking. Let's look at the kinds of questions you'll see. So you've got this one here, titration, which titration curve matches the situation described below. So this would be weak acid with a strong base. Go ahead and do it. Let me move this over here a bit. Okay, so weak acid titrated with a strong base. So we'll have pH over here, and we're adding strong base, so it'd be volume of what, acid or base, is going to go on the x-axis. What's going to go on the x-axis? Volume of what? Acid or base? Remember, there's plenty of answers here. Could be volume of acid, could be volume of base. Any ideas?
It would be a weak acid.
No, but I mean, what goes on the x-axis? What are we adding? Are we adding the strong base or the weak acid? Well, what's in the flask and what's in the burette?
Is it volume of base at the bottom?
It is, yeah, because the acid is in the flask and the base is in the burette.
I read that the opposite way. That's my bad.
Okay, so weak acid with strong base. So we know it goes base on the bottom. Is everybody okay with that? Anybody have any questions? Okay. The next thing we need to do, and this is base. So I'm actually going to say strong base just for kicks here, but I don't really need that. But I know it's going to be strong. So we're starting out. The weak acid is going to be a pH of 5, and we're going to end with pH of 14. Is everybody okay with that? Starting at a pH of 5 and ending with a pH of 14. Everybody okay? So let's look at what the curve's going to look like. So the start is going to be, that's going to be start, and that's going to be finish. It's going to look like this. And now I've got to figure out if we're going to have a buffer region or not. And for buffer region, we'll have if we've got a strong base being added, which we do, and we do have a weak acid here. So I would expect the buffer region. So that would be my answer. Remember, buffer regions only occur when we're adding a strong acid or strong base from the burette. Does anybody have any questions? So which one would it be? Let's see if I can find it. It has to start out at 5 and has to have a buffer region. There he is. That's the one. So a lot of answers here. It's hard to guess. You'd have to know what you're doing, I guess.
So you said the buffer region only occurs when you're adding a strong base or a strong acid?
Yeah, it's strong base or strong acid to a weak base or weak acid.
Okay.
All right. That's just a quick and dirty way of doing it. You'll understand buffers a lot more when we get into buffers, which we'll get into probably in a week or two. Okay, now question 2. This is the one that people hate. Oh gosh. I wish there was an easy way to study this one. Anybody got any ideas about, I mean, this is a horrible question. People hate it. They really do. They really hate this question. They detest it. I get hate mail for this question. I do. People email me hateful stuff because of this. Gosh, I wish there was an answer. Can anybody come up with a way that they might study for that question? Any thoughts? No thoughts? Nobody has any ideas?
I mean, just constant practice.
How might you practice it though? I mean, what kind of resource might you use?
Oh, thank you for asking. You got the videos, you have the tests, you have like a couple past tests.
This specific question though, how might you study just for this specific question too?
Personally, I look at the videos that you send.
Okay. But with this one though, you can just do this question again and again and again and again. And you'll get a different question every time. And you can practice it and you can make sure you're understanding the pattern. That's how I would do it. There's no excuse really. I mean, people, you can say whatever you like at the end. Oh, Dr. Musgrave, you don't give me enough resources to be successful in this course. Sorry. I ain't buying it. Oh, Dr. Musgrave, you're not transparent enough. I don't know what's going to be on the test. Nope. Sorry. That one doesn't fly either. It really boxes you in. You know, it's just no way that you can blame me. I'm sorry, you can't. All right, let's take a look at this one then. I've got SB being strong base and CH3COOH being weak acid. You don't know what's being added to what here, but it doesn't really matter because whatever's being added to what, we're always going to end up with the same equivalence point. And the same thing's going to be there at the equivalence point. So let's see how we might deal with something like this. All right, CH3Li and CH3COOH. Now, so we know this is a strong base. We know this is a weak acid. Given that it's a weak acid, don't know how to split this. It's going to be CH3COO minus and H plus. And as I had said earlier with the strong base, if you've got a metal ion, then you just split it up this way to be CH3 minus and Li plus. I'll stop here for a second. Does anybody have any questions about what I've done so far? Now you might be wondering, how do I know what the charge on the Li is? Well, if you look at the periodic table, it's in group 1. I don't really want to pull one up here, but it's in group 1, so that's how we know it's got a 1+ charge. The other thing I can tell you is that I don't think there's any examples of anything that has a 2+ charge anywhere, so you know that any metal ion you're dealing with here is going to be 1+. So what's going to combine with what? Well, the negative is going to combine with the positive here. That would be CH4. And the Li will combine with the other thing here, CH3CO. So what do we, it says treat subscripts and superscripts as normal. Do not leave any spaces. Yeah, so in the box, this is what you would write. It would end up being like this, CH4 plus Li CH3COO. Now the CH3, the LiCH3COO should be expressed like that because it goes cation first and then the anion for a salt. So that's what I would do. Is if I was, I mean, like I said, people hate that question. They detest it until they understand it. Eventually they twig. They say, "Oh, I see. It's not that bad." But initially, it looks awful. So that question on the pen and paper test, typically half the class gets it wrong. Typically, half the class gets it wrong because people just do not take the time. They do not take the time to understand it. Well, I'm not giving you a choice. You have to understand it, which means you'll have to continually do it until it sinks in. I'll drag you through it. I'll drag you through this by the hair if I have to. Hundreds of thousands of students have understood this before. You can do it too. You're not the first people to be exposed to this. This is not something that's unique to my class either. You might think, oh yeah, he just makes up this stuff and just to annoy us and nobody else ever has to deal with it. That ain't true. Which indicator is the best to use in the following titration? So strong base with weak acid. So what do you have to do there? Well, you have to figure out what the pH or the equivalence point is. That's easy because you've got strong base. Strong base is 14. Weak acid is 5. And divide that by 2 and you get 9. And then you'll go with phenolphthalein as your answer. So question 3 is easy. All right, anybody got any questions about question 3?
I don't have a question, but can you just leave it there for a second so I can write that down?
Oh, sure, sure.
Thank you.
Anybody have any questions? Can I re-roll here on the somebody else? Yes. Can I re-roll? I'm going to re-roll. All right. This is what you can do to study. I'm going to submit that. You can do the same thing. And And here we go. We're going to re-roll, and we're going to do question 2 again. In fact, I'm going to make you do it. Ha 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 ha. Oh, sorry. Sorry. There we go. All right. So that one's pretty easy. Once you do that one, just give it a go. That one's an easy one though. Give it a go. All right. So let's see how we do that one. Okay. All right. So KOH, it's a strong base, and we've got HNO2. It's a weak acid. Weak acid will make H plus, NO2 minus. The KOH will do K plus and OH minus. So the OH minus combines with the H plus, that gives us water. And the K plus combines with the NO2 to give KNO2. So that's what you should have had. Anybody have any questions about that one? All right, let's re-roll. Showing this exit preview here, I don't need to do it. Oh, this one's a good one. I like this one. All right, why don't you try this one? Try this one, please. Oh, yeah, this one's a good one. Oh, yeah, I like it. Yeah. I lost one. All right, now down to 7. I do appreciate you all being here today, by the way. I know that some people are going to watch it, and I know some people have really good intentions of watching it, but won't. It's worth it, though, folks. It's worth it. Okay, let's have a look. CH3Li. CH3Li and LiHSO3. Oh, okay, so he's a strong base, and he's a weak acid. So weak acid, we make it H plus and then LiSO3 minus. And on the other side, we'll have CH3 minus and Li plus. So the CH3 minus combines with the H plus, that'll give us CH4. And then the Li plus combines with the LiSO3 minus to give Li2SO3. Does anybody have any questions?
I got that one, but could we do number 3? Sorry, number 3 again.
Oh, number 3?
Yeah.
Okay. All right. So strong acid with a strong base. So the strong acid is going to be pH of 1, strong base pH of 14. The equivalence point is going to be the average of those, which is going to be 7, which makes it phenol red. Is that okay?
Yes.
It's really that easy. You know, as long as you know the pH ranges for strong acids, strong bases, weak bases, I don't see how one can go wrong with number 3. You know, that one's not too bad at all.
So all you do is get the like pH range of each and then put them together?
Yeah, divide them by 2. Yeah.
Okay.
Because that's how you get an equivalence point. It's just going to be the average of the 2, right?
Okay.
Oh, let's re-roll. These are fun, aren't they? Oh, I tell you, people hate this question. They hate it. They go, oh, God, no. It's not that bad. Gosh, not that bad. Yeah, let's try again. Let's see, number 2. I'm enjoying this just a little bit too much, aren't I? No, that one's too much like the one we just did. I'm going to re-roll again. I don't like it. We've already done something like that. It was different, but we've already done something like it. Let's do something different. No, it's not too bad. Yeah, okay, let's do that one. So we've got a strong acid, a strong base, HClO4, KNH2. All right, see what you end up with. All right. So we've got HClO4. Let's move that over a little bit. Which is going to be H plus ClO4 minus because it's a strong acid. And the other one, KNH2, to be K plus NH2 minus. And that's going to be our strong base. The K plus combines with the ClO4, the H plus combines with the NH2 minus. We're going to have NH3 plus KClO4. Any questions? Any questions? All right, let's re-roll.
I have a question. Like, I'm really getting confused with how you break them apart. Like, I understand after you put everything together, but breaking them apart, that's what I'm having issues with.
Okay, well, the acid will always have H plus every single time. And then when it's, sorry, start again. Let's take a look. So for something like this, you know that the weak acid will break into H plus, and then whatever's with it will be negative. So that'll be NO2 minus. And for the other one, you know that the metal will be K plus, and whatever's with it will be minus. That's how you're breaking it apart.
Okay, thank you.
Yeah, is that okay?
Yep, I got it.
Okay, that one's pretty easy. I don't want to do that one. Let's do another one. Yeah, you know, sometimes you get an easy one, sometimes you get a hard one. All right, well, this one, all right, so we don't have a metal ion here. All right, so this one's a little bit different, isn't it? All right, so what, if you don't have a metal ion, what would you do with this one? Any thoughts? We know the acid's easy. I mean, that's going to be H plus. Oops, sorry about that. The acid's easy. That's going to be H plus and NO3 minus. No problem with that. Strong acid. Now the weak base, there's no metal ion here. How would you break that apart? And how would you know to break it apart the way you're going to break it apart? Any thoughts?
You have the hydroxide there, so it's kind of a giveaway.
Yeah.
OH.
Yeah. So you know that that's going to be OH minus, which means the rest of it's going to be NH4 plus. So the H plus combines with the OH minus, gives water, and then the rest of it combines together, NH4, NO3. That would be the answer. So yeah, so that's, but again, look, you might say, well, gee, Dr. Musgrave, that's not fair. You know, that's different from, look, the thing is, you have the opportunity. You can take this test as many times as you want. You'll see this example. And if it's the same test, so, you know, eventually, if you have questions, you can always email me. You know, you turn up with your pitchforks and torches and whatever. That's fine. It's not fair, Dr. Musgrave. It's not fair. All right. Anybody got any questions? All right. That's it. That's all I wanted to go through today. For the rest of you, hopefully I'll see some of you in lab. I don't know, maybe 6 of you. I'll see some of you in lab, and I'll catch the rest of you later on. All right. So I'll see you all Thursday, if I don't see you in about 15 minutes.
All right, see you later.
Bye.
Bye-bye. Thank you.
Mary, you all right?